Hello and welcome to Lecture 8, Forces 2. In this lecture, we're going to go over Newton's second law, and then we're going to practice some problems using Newton's second law. We're also going to practice problems that where the object is on an inclined plane, making it a little bit tougher. All right, so Newton's second law. So Newton's second law is just this equation here, which is F net equals ma. So I'll just highlight that for you. All right, so this tells us that if there is a net force acting on an object, then it will accelerate in the same direction as that of the net force. So remember when we looked at Newton's first law, it said that if the object has no net force acting on it, it will not accelerate. So that means it will remain at the same velocity forever. If the object was initially at rest, it will remain at rest forever. If the object was initially moving 1 meter per second north, it will continue to move 1 meter per second north forever. But if there is a net force acting on an object, so an unbalanced force, where all the forces acting do not cancel each other out, you'll have a net force, which implies that you'll have an acceleration. And the direction of the acceleration will be the same as the direction of the net force. Okay, when you want to solve for the acceleration, you can just divide both sides by mass, and you'll end up with this equation here. Acceleration equals F net over mass. Okay. So recall that F net represents the sum or the total of all the forces acting on the object. All the forces acting on the object. So if you're unclear about what that means, you might want to review the vector addition lecture to go through those problems again. Okay, but we're going to go through that again today. We're going to do some questions that involve the last lecture's material, Newton's first law. We'll be looking at drawing free body diagrams and calculating all the forces and finding the net force. And then so today's lecture is about Newton's second law, where we're using A equals F net over mass to find the acceleration. And then we'll take a look at some kinematic equations to solve for unknown values. Once you have the acceleration using Newton's second law, you can find unknown values in kinematic equations. So that's what we're going to be doing today. Okay, so let's start off with question 1. You're pushing a 35 kilogram box across the floor with a force of 45 newtons. The coefficient of friction between the box and the ground is 0.08. So we'll begin by drawing a free body diagram of the box. Okay, so this is part A. So to represent the box, we're just going to draw a simple dot here. And now we need to think about what are all the forces that are acting on the box. Okay, the first force that should always come to mind is the force of gravity, which always points straight down. So here's my force of gravity. The box is on a horizontal surface. It just tells us that it's on the floor. It doesn't tell us the floor is inclined at all, so we need to assume that the floor is just a horizontal flat surface. So because the object is resting on a surface, there'll be a normal force, and the normal force will be perpendicular to the surface, so it will be vertically pointing upwards. Okay, the normal force keeps the box from falling through the floor. All right, it says you're pushing the box across the floor with a force of 45 newtons. So there's an applied force there. You pushing the box means that there's an applied force. Let's say that you're pushing the box to the right. Then that means that the applied force would be pointing to the right. Okay, it doesn't tell us which way it's pointing, so we're just going to make an assumption. It doesn't matter which way we choose, left or right. And then we have the coefficient of friction is given. So because the coefficient of friction is given, that means that implies that there is a force of friction acting on the object. If friction wasn't mentioned in the question, we can pretend that there was no friction acting. But because it's mentioned, we know that there has to be a force of friction. We know friction always opposes the motion. So the object was just sitting there. We are pushing it to the right. Friction opposes the motion, so since the object is moving to the right, friction must be pointing to the left. So here's our force of friction. Okay, let's take a look at the length of each of these vectors that I drew. So notice the force of gravity and the force normal should be equal length. They're the only two forces that are acting in the y direction, the vertical direction, and they should be canceling one another out because we know that this box is not accelerating vertically. It's not flying up into the sky or falling down into the ground or anything. It's not moving vertically at all. So the forces in the y direction should cancel out. There's only those two forces, so they must be equal to each other in magnitude. So the length of those vectors should be approximately equal to each other when I draw it. Now we have force applied and force of friction. We know that the net force should be pointing in the direction the object is accelerating. The object should be accelerating to the right because we're pushing the box to the right. It should never be accelerating towards the force of friction because originally the box is at rest, and it tells us that in part E. It's originally at rest, so our force of friction should not be making it move to the left. It's like if you're pushing a piano forward and there's friction between the piano and the ground pointing backwards, that friction will never be bigger than the force that you apply, so the piano would never be moving backwards onto you. It will always be either moving forward, or if the two forces are equal, it would just stop accelerating altogether. Okay? So the way that we've drawn this, we want to keep in mind the length of our vectors should represent the magnitude of each of these forces. So if the two vectors should be equal in length, that's because the two magnitudes should be equal in magnitude. Okay, so let's move on to part B, where we start to calculate the forces. Every time we calculate the forces on a free body diagram, we should always just begin with Fg, because Fg always just equals mg. It doesn't matter what the diagram looks like, Fg is always mg. So let's plug in what we know. Our mass, this is the box, so it's 35 kilograms. And g is 9.80. And that would be meters per second squared, which is equivalent to newtons per kilogram. I'm going to write newtons per kilogram so that you can see the units canceling out. And so we're just left with Fg is equal to 35 times 9.80. I'm going to type that on my calculator, and I get 343 newtons. So that's my Fg. Moving on to F normal. We know that F normal has to cancel out with that Fg. Those are the only two forces acting in the y direction. So F normal should also equal Fg. F normal then is 343 newtons. Okay, once we know F normal, we can find force of friction, because the force of friction is always equal to the coefficient of friction times the normal force. So we can't find force of friction until we know the normal force. So our force of friction is equal to the coefficient of friction, which is given in the question as 0.08, times the normal force, 343 newtons. Force of friction is equal to, let's type that on our calculator, 0.08 times 343 newtons, and that's 27.44 newtons. The one other force that's here is F applied. And F applied was just given in the question. It tells us that you're pushing the box with a force of 45 newtons. So F applied is 45 newtons. All right, so now we know all of our forces. In part C, we're asked to find the net force. So let's do that. So when you're looking for the net force, you need to consider both the x, or the horizontal direction, and the y, or the vertical direction. We've already talked about the y direction. The normal force and the force of gravity have canceled each other out because we don't want this object to accelerate vertically at all. The object's not even moving vertically. It's only moving in the x direction. So in order for the normal force and the force of gravity to cancel out, that means the net force in the y direction is 0. So we can just ignore that one. Let's move on to the x direction. The F net in the x direction. Let's pick a direction that we want to be positive. The positive direction, let's say, is pointing to the right. Okay, so our net force in our x direction, what would it equal if positive is to the right? We only have two forces that have x components, F applied and force of friction. F applied is positive and force of friction is negative. So let's write that in. The net force in the x direction would be F applied minus force of friction. So my F applied we said was 45 newtons minus the force of friction, which we found was 27.44 newtons. So I'm just going to subtract those two, and I get 17.56 newtons. Now the answer is positive, and we said positive is to the right, so I'm just going to put a little arrow to indicate this is moving to the right. The net force in the x direction is pointed to the right. Okay, so that's C. D is asking for the acceleration of the box. So this is where we begin to use Newton's second law, which is F net equals ma. Now we're looking for acceleration, so let's rearrange the equation. Dividing both sides by mass, we get F net divided by mass. So if we're looking for our acceleration, it's equal to the F net, which we found was 17.56 newtons. And that was pointing to the right, so I'll just put a little right here to remind us which way it was going, divided by the mass, and the mass was 35 kilograms in the question. So our acceleration is 17.56 divided by 35, and we get 0.5017 newtons per kilogram, which is equivalent to meters per second squared. Okay, and again, that's moving to the right. All right, so we've done A through D so far, and now we can move on to part E. In part E, the question is giving us some variables. The box is initially at rest. How long would it take for it to travel 25 meters? So it's asking us to use a kinematic equation to solve for the amount of time it takes to travel a certain distance. Okay, let's write down everything that we know here. So the box is initially at rest, so that means that the initial velocity is 0 meters per second. How long will it take? So that means they're asking for the change in time. How much time does it take to travel 25 meters? That's the distance traveled, which would be delta S is 25 meters. Remember that in all the kinematic equations that we have, they all require acceleration. That's why we had to complete part D to find acceleration first in order to get to part E. Okay, so the acceleration from part D was 0.5017 meters per second squared. So now we should have enough information if we use a kinematic equation to solve for delta t. We first have to decide which equation to use. So what is the one variable that's not listed here that we're not trying to find and we don't know? It's v final. Okay, so v final is the one variable that we don't know and we don't care to know. So we're going to choose the equation that doesn't have v final in it. That's the first kinematic equation, which is s final equals s initial plus v initial delta t plus 1/2 a delta t squared. Now remember, if you move the s initial to the other side of the equal sign, we get s final minus s initial, which is the same as delta s. So I'm going to just rewrite the equation this way now. I'm writing it like this because the question gives us delta s, so I want delta s in my equation. All right, we're solving for delta t, but delta t is written out twice, once as just delta t and the other one delta t squared. So we can't isolate for it yet, so we're going to just substitute in the values that we know. Delta s is 25 equals v initial is 0. Delta t is what we're looking for, plus 1/2 a is 0.5017, and then we have delta t squared. Let's simplify this a little bit. 0 delta t is just 0. And now we have 1/2 times 0.5017, which is I typed that in wrong, so I'm going to do it again. 0.5 or 1/2 times 0.5017, which is 0.25085 delta t squared. I'm trying to solve for delta t, so I want to divide both sides by that decimal there. So they cancel out, and now I'm left with delta t squared on the right side, which I'm just going to move over to the left side, equals 25 divided by 0.25085, and I get 99.661. Now I want to get rid of the squared, so I'm going to square root both sides, remembering that plus or minus that goes in front. So when I square root delta t squared, those two cancel, and I'm just left with delta t is equal to the square root of 99.661, and I get plus or minus 9.983. Okay, but now remember that this is time, and there's no such thing as negative time. So I'm not even going to put in the minus at all. I'm just going to write delta t, the change in time is 9.983, and I'll put in the units, seconds. Okay, so the question was asking how long would it take to travel 25 meters, and the answer is 9.983 seconds. All right, so that was question 1. It's quite a long process here. We're going to try this again with question 2. All right, so you're pulling your baby sister along a level road on a sled. You've been walking at a steady 1.5 meters per second, and the rope pulls up on the sled at a 30-degree angle above the horizontal. If the combined mass of your sister and the sled is 60 kilograms, and you're pulling with a force of 75 newtons, what is the coefficient of kinetic friction between the sled and the snow? Okay, so for these problems, even though it's not actually asking you to do this, you always want to start by drawing a free body diagram of this, okay? And in this case, you're pulling your baby sister along a level road on a sled. The object that you're drawing a free body diagram of is the sled with your baby sister on it. Okay, so here's my dot, which represents the sled with my baby sister on it. What forces are acting on the sled? So you'll always have the force of gravity, which points straight down. Okay, the sled is on a level road, which means it's a horizontal road. So that means the normal force will be perpendicular to the surface, pointing straight up. So that's my normal force. The rope is pulling up on the sled at a 30-degree angle above the horizontal. So here's my rope pulling 30 degrees above the horizontal. What type of force is that? There's a rope and it's pulling. Okay, so that would be the force of tension. Okay, you're also pulling on the rope. You're the one pulling, and you're pulling with a force of 75 newtons. If you wanted to, you could also call that force the applied force, and that would be fine as well. But since it's a rope, I'm going to call it tension. And then The question mentions the coefficient of friction. It's asking you what is the coefficient of kinetic friction between the sled and the snow. So because it's asking you for friction, you know that there is friction in the problem. So now you just need to think about which way is the force of friction pointing. So if you think about yourself pulling a sled, even though the rope is on an angle and you're pulling upwards like that, the sled is still moving along the ground. So it's still moving horizontally. So this sled is moving towards the right. And so the force of friction should oppose the motion and therefore move to the left. So here's my force of friction. Okay, so there's my free body diagram. Next, I want to actually calculate all the forces. So let's begin with force of gravity because that's always the easiest one since Fg always just equals mg. So the mass is the mass of the object I drew the free body diagram of. That would be the sled with my baby sister on it. And it tells us in the question their combined mass is 60 kilograms. Ng is 9.80 newtons per kilogram. Kilograms cancel, and I'll type this onto my calculator. 60 times 9.80, and I get 588 newtons. All right. So next we want to find normal force, but this time, does the normal force equal the force of gravity? Well, if it did, we would still have a y component of the tension force, which would cause my sister and the sled to fly upwards and accelerate up into the sky. And we don't want that to happen. We want all of the y components of all the forces to cancel each other out. So what I'm going to do is decompose this force of tension here. And I'm going to call this one Tx and this one Ty. Okay, so let's find out what Ty is so that we can use it to find the normal force. Okay, the tension force was given to us in the question. You're pulling with a force of 75 newtons. That's the tension, which is the hypotenuse here. How do I find the Ty? Well, Ty is opposite of 30 degrees, which means I would be using sine. So it would be 75 sine of 30 degrees. Okay, so I'm going to type that into my calculator. And I get 37.5 newtons. All right, so that's my Ty. So if I know what my Ty is, I should be able to figure out my normal force. And that's because all of the forces acting in the y direction should all cancel out. So I'm going to write it like this. I'm going to say up is positive, and the net force in the y direction should equal 0. Okay, and they equal 0 because we know that the object is not accelerating in the y direction. So what are all the forces acting in the y direction? We have the normal force, which is what we don't know. We have Ty, which is positive because it points upwards. And then we have Fg, which is negative because it points downwards. So let's solve for normal force. We'll bring the Fg to the other side, making it positive, and the Ty to the other side, making it negative. And we're left with the normal force equaling Fg, which we already found was 588 newtons, minus Ty, which was 37.5 newtons. So I'm going to type that on my calculator, 588 minus 37.5, and I get 550.5 newtons. So now I know my normal force. And what this is saying is that all the forces that are pointing upwards, so F normal and Ty, okay, those should cancel out with all the forces pointing downwards, Fg. So if I added up Fn and Ty, 550.5 plus 37.5, I should get a number that's equal to Fg, 588, because those forces should all cancel one another out. Okay, so now I know what my F normal is. Next, I want to find my force of friction. Okay, so how am I going to find my force of friction? Normally, I would say the force of friction is equal to the normal force times the coefficient of friction. But in this question, it's asking us for the coefficient of friction. That's what the question's asking for. So we need another way to find our force of friction. And for that, we need to be very careful when we're reading the question. There's a key word there that's very easy to miss. It says you're pulling your sister along a road on a sled. You've been walking at a steady 1.5 meter per second. What does that mean, that it's a steady speed? It means it's a constant speed, which implies that the acceleration is 0. So that means that in the x direction, your acceleration is 0. And since F net equals ma, if the acceleration is 0, then that means your F net in the x direction should also be 0. So it's similar to what we did with F net y equaling to 0. We're going to do the same thing, but with F net x equaling 0. So I'm going to say positive is to the right, F net x is equal to 0. So what forces are acting in the x direction? We have Tx, which is pointing to the right, and we have Ff, which is pointing to the left. Okay, so my F net x would equal Tx, which is positive, minus my force of friction, which is negative. All right, so all that equals 0. Now I need to know what is my Tx equal to. So Tx is the adjacent side to the 30-degree angle, so I'm going to use cos. So it will be 75 cos of 30 degrees minus Ff equals 0. I can move my Ff to the other side of the equation, so I get 75 cos 30 degrees equals Ff. So Ff, I'm just switching the two sides now. Ff is equal to 75 cos 30 degrees, and I get 64.95. So now I know my force of friction as well. Perfect. But the question's not asking for force of friction, it's asking for the coefficient of friction. Okay, so let's think about the formula to find the coefficient of friction. So remember, if we're looking for the force of friction, it equals the coefficient of friction times the normal force. Well, we've already found the force of friction, and we've already found the normal force. So we should be able to rearrange that formula to get the coefficient of friction. We're going to divide both sides by F normal so that we isolate for the coefficient. And so we're left with mu, which is the coefficient of friction, is equal to Ff divided by F normal. And now we can sub in what we know. So our coefficient of friction is equal to Ff, which is 64.95 newtons. Let's put in the units here. Divided by the normal force, which is 550.5 newtons. Let's divide that out. 64.95 divided by 550.5, and I get 0.118. Notice newtons cancel out. Coefficient of friction has no units. And that's my final answer there. Okay, so again, quite a long process, and there's a very important keyword here to keep in mind if you see something like that. If it's moving at a steady speed or a constant speed, then you know that the net force acting must be 0. And so you can solve for missing values of forces using that information. Okay? All right, let's move on to question 3, our final question in this lecture. Now, so far, the free body diagrams that we drew for the two previous questions were for objects that were resting on flat horizontal surfaces. But now we're going to practice a problem where an object is on a ramp. Okay, and we're going to do something similar to what we did in the previous questions, except the object is on a ramp, making it a little bit more challenging. Okay, so let's begin. A 5 kilogram block is placed on a ramp which is inclined at 12 degrees and begins sliding down. The coefficient of friction between the ramp and the block is 0.12. Draw a free body diagram of the block. Okay, so let's begin with that. So let's draw a ramp. And it's inclined at 12 degrees. So we have a block resting on the ramp. So let's just change the color here. So this is my block. I'm representing this as a dot. And what are all the forces acting on this block? So as always, we have a force of gravity that always points straight down. Because the block is on a surface, there's going to be a normal force, but the normal force is always perpendicular to the surface. So we need to draw a force vector that's perpendicular to the ramp itself. So it would look sort of like this. Okay, so that's my normal force. There's also mention of friction. So the block is placed on the ramp. So which way is the block going to move? It's going to move down the ramp. It tells you even in the question. It begins sliding down the ramp. So friction, since it's mentioned, we have to include the force of friction. Which way is it going to go? It always opposes the motion. So since the block is sliding down the ramp, friction must point up the ramp. So here's my force of friction. Okay? Are there any other forces here that are acting on the block? There's no applied force because nobody is pushing or pulling it. There's no tension because there's no rope here at all. Okay, so that's it. All right, so that was part A. Now let's move on to part B. Calculate all the forces. So as always, we're going to start with Fg. Fg is equal to mg. The mass of the block is 5 kilograms. And G is 9.80 newtons per kilogram. Kilograms cancel one another out, and I get Fg is equal to 5 times 9.8, which is 49 newtons. Okay. Now we need to find our normal force. Okay, we find the normal force before the force of friction, since the force of friction is equal to the coefficient of friction times the normal. We can't find it yet until we know the normal force. But how do we find the normal force here? It's not going to cancel out with the force of gravity because they're not opposite to one another. They're not opposing each other. The normal force is on an angle. Let's think about which direction is the block moving. The block is moving down the ramp, right? It's going this way, down the ramp. It's not moving this way. Sorry. It's not moving this way at all in that direction. So since the block is moving down the ramp, we're going to say that down the ramp like this is the x direction. And we're going to say that the perpendicular direction, which is like this direction here, is the y direction. Okay, so the block is moving along the x direction. It is not moving along the y direction at all. So what does that mean? It means that the block has no net force acting on it in the y direction. Now we know the normal force is pointing in the y direction, so there has to be another force that cancels out with it along that has a y component. What force would that be? It would be that force of gravity that's there. We can decompose the force of gravity to have a component that's parallel to the y direction and a component that's parallel to the x direction. So this would be the Fgy because it's in the y direction, and this one would be Fgx because it's in the x direction. and the hypotenuse, which is drawn in black, is the FG. Okay, so before we can actually find the components, we need to know what angle is in that triangle. So that gets a little bit tricky. We know that there's a 12-degree angle down here at the bottom of the ramp. How does that end up in the triangle? It's actually going to be one of the two angles. We know this angle here, the third angle, is a 90-degree angle because x and y directions are perpendicular to each other. So where does that 12-degree angle go? It's getting a little bit messy, but I'm going to try to do it on this graph so you can see. So I'm going to extend this to make it into a triangle. This triangle here is a 90-degree triangle. If this is 12 degrees, how would we find the angle up here? Well, we know that all the angles in a triangle add up to 180 degrees. So we have 90 degrees, 12 degrees, so the other angle must be 90 minus 12 degrees, okay, because we already have 90 degrees here. And if they all are to add to 180, then the other two should be 90 put together, so that the 90 plus 90 is 180. So how are we going to find this missing angle here? It would be 90 minus 12, which is 78. Okay, if you add up all these angles now, you'll have 180 degrees. Every triangle should have a total angle of 180 degrees. Okay, so now if this is 78 degrees, notice that this is a 90-degree angle here as well. So how do we find the angle that's inside that triangle? Right here. If they add up to 90 degrees, then if one is 78, the other one must be 12. Okay, so when you do questions like this, you'll always find that this angle is the same as this angle here. Okay, so I just wanted to show you how to figure that out on your own. Okay, so now we know what the angle is inside that triangle, so we should be able to find out what FGY is. So let's find that out next. FGY. So FGY is adjacent to the 12-degree angle, and the hypotenuse is FG, which is 49. I'm just going to put that 49 Newton in right here. So then that means that FGY would be 49 cos, since it's adjacent, 12 degrees. So we have 49 cos 12, 47.93 newtons. Okay, so now we know what FGY is. So we can also find out what FGX is, so let's do that right now. So FGX is opposite of the 12-degree angle, so we're going to use sine instead of cos, so it's going to be 49 sine of 12 degrees. So let's type that up, 49 sine of 12 degrees, and I get 10.19. All right, so how are these going to help us find out what the other forces are? We're going to look for normal force next. If we look at the y direction, which is on that angle that's denoted by that red y direction line there, we can see that there's really only two forces that are acting in that direction. We have F normal and we have FGY. Those are the only two forces that are in the y direction. So those need to cancel each other out because we know that this object, this block, is not accelerating in that direction at all. So that means that the normal force and FGY must cancel one another out, meaning they have to be equal to each other in magnitude, moving in opposite directions. So if FGY is equal to 47.93 newtons, then that means that the normal force must also equal FGY. So it also has to equal 47.93 newtons, because they're the only two forces that are in the y direction. Okay, so now we have for all of our forces listed. except for a force of friction. But since we know normal force, we can figure out the force of friction, which is equal to the coefficient of friction times the normal force. So our force of friction is the coefficient of friction, which should have been given in the question. It's 0.12 times the normal force, which is 47.93 newtons. So I'm just going to multiply those, 0.12 times 47.93, and I get 5.75 newtons. All right, so now I know what all of my forces are. I know force of gravity, I know Fgy and Fgx, so I decompose my force of gravity into x and y components. I know my normal force, and I know my force of friction. All right, so I can move on to part C. Find the net force. All right, so which direction is going to have a net force acting on it? The x direction or the y direction? We've already said that in the y direction, the forces have to cancel each other out because the object is not accelerating in that direction at all. It's not even moving that way. So we know that the net force is only going to be in the x direction. So I'm going to decide which way I want positive to be. I like making the positive direction the direction the object is actually moving. So I'm going to say positive is going down the ramp, which kind of looks like that. It's going that way down the ramp. And then I'm going to write F net in the x direction is equal to, now what forces are acting in the x direction? Do we have anything that's pulling the object down the ramp? So it's Fgx. Fgx is pulling the object down the ramp. So that's positive because it's going in the positive x direction. And then we have a force that's opposing that motion, which is force of friction, so it's going to be a negative. So I have the net force in the x direction is Fgx minus Ff. Remember that force of gravity, the one that's written as a black vector, okay, so this vector over here, this one has been replaced by the other two vectors, the Fgy and the Fgx. So now that we've replaced them, we can pretend that that Fg, the black vector pointing downwards, has disappeared because it's been replaced. Okay? So now let's write down what we know. F net in the x direction is equal to Fgx, which we found previously to be 10.19 newtons, minus force of friction, which is 5.75 newtons. Okay, so let's just type that up on our calculator. 10.19 minus 5.75, and I get 4.44 newtons. Okay, since it's positive, that means that it's moving in the positive direction. We said positive is going down the ramp, so that's the direction that the net force is moving. Perfect, so that was part C. Remember that force is a vector, so we have to say which direction it's going. I could just do the arrow if I want, like I did here, or in brackets I could say down the ramp. Okay, whatever you prefer. Part D, determine the acceleration of the block. So I'm going to do that right here, part D. So remember F net, using Newton's second law, F net equals ma. If I'm solving for a, I'm just going to divide both sides by mass, and I get a is equal to F net divided by mass. So my a is F net, which was 4.44 newtons, divided by my mass, and my mass was 5 kilograms. Given in the question, let's move up to see that. It was a 5 kilogram block. Now I'm going to just type this on my calculator, 4.44 divided by 5, and I get 0.888. The units are newtons per kilogram, which is equivalent to meters per second squared. And the direction would be still down the ramp. Okay, because the F net was going down the ramp, so the acceleration is in the same direction. So that was D. So now we can finish the question off with part E. How far does the block slide after 2.4 seconds? So how far does the block slide? So that's my delta S is what I'm looking for. That's my question mark. After 2.4 seconds, so that's my change in time, is 2.4 seconds. I know from part D that my acceleration is 0.888 meters per second squared. And let's take a look at the question to see if there's any other information. It says an object is placed on a ramp. So what does that imply if the block is placed on a ramp? Okay, it's not pushed down the ramp, it's just placed there. So the initial velocity of that block is 0. Okay, so we're going to use a kinematic equation that doesn't have V final in it because there's no V final listed here. So it's going to be the first equation, delta S equals V initial delta T plus 1/2 A delta T squared. Delta S is what we're looking for. So I'm going to just sub in all the values that I know. 0 times 2.4 plus 1/2 A, which is 0.888, and then delta T, which is 2.4 squared. And I'm just going to type this all up on my calculator. 0 times 2.4 is just nothing, so that's gone. So I have 1/2 times 0.888 times 2.4 squared, and that gives me 2.56 meters. So the distance that it travels is 2.56 meters. So that was our final question. All right, so these questions are all quite long. Make sure that even if the question is not asking you to go through these steps as it did here, A, B, C, D, and E, you still really have to go through all of these steps in order to get to the final answer. How far does the block slide after 2.4 seconds? Okay, so don't try to skip steps. You want to make sure you're starting off with drawing your free body diagram correctly, finding all of the forces, using them to find the net force, using Newton's second law, that equation F net equals ma, to find the acceleration. Once you have your acceleration, you can then use a kinematic equation to solve for the unknown value. In this case, it was delta S. Okay, so I hope that helps. Thanks so much for watching, and I'll see you next time.